Okay, so we're going to start something new today. I posted something on Canvas about the Lagrangian points. Again, I don't know if we'll have time to see them, but there was a question, very good question last time about orbits around the Earth that may look like the satellite is maybe in line between Sun and the planet. They do exist. They're very far. The James Webb Telescope will actually take one of those points in the future. So I will show you something on the projector towards the end, and also how those points are located with respect to the Earth and the Sun. But we are going to start something else. Orbital maneuvers. So as far as I'm concerned, we're really starting to do cool stuff. Ground tracks, predicting where the ISS is going to be. Now we're going to start changing orbits, which to me is really cool stuff. I don't know how many people can understand these things we're talking about. Very few. So what are maneuvers? Well, it's you somehow, usually with thrusters, but it's not always the case, but that's the most common approach. You trying to change something on your orbit, either its size, its orbital plane. Last time we've seen how you can use nature, the J2 perturbation, to actually change the orbital plane. You can call that a maneuver. It's just happening naturally. You're changing one orbital parameter in particular in a way that you desire, but that is happening through a natural effect. Other ways to use nature to change the orbit are, if you're in low Earth orbits, you can use the drag force to maneuver, for example, satellites with respect to each other, or even just a single satellite to do something while it's decaying through the atmosphere. Patrick, I will show you at some point some of his work on solar sailing. So you can use nature to perturb an orbit and actually call that perturbation a maneuver. But for the most part, we use thrusters. You use the principle of the third law of Newton, action-reaction. You push out mass, hot gases at high speeds, and you get a push in the other direction of response, right? That's how we get into orbit, and that's how we usually maneuver once we're there. So I'm going to try to classify maneuvers. Very first classification I can give you is a drastic maneuver. Something that really requires a lot of thrust, can be going into orbit, but that's something we're not seeing in this class. We assume we are already in orbit. So an example could be a pretty obvious one. You are in Leo and you want to go to an interplanetary trajectory. So you want to leave this planet, go from a possibly circular low Earth orbit to definitely some hyperbolic path, and then eventually do something else to approach Mars, for example. That is something that is going to require a strong, intense thrust applied to your spacecraft. Or you could have the other end of the spectrum, which is, what did I call it? Minimal or mild, I guess. What is an example of maneuvers that are very minimal, that you can imagine, that we do on a regular basis? Otherwise, the astronauts on the ISS just die of starvation. Rendezvous, for example, right? What the shuttle used to do, approaching the International Space Station, what the ATV from the European Space Agency and the HTV from the Japanese Exploration Agency, and all those refueling modules that go up, once they get pretty close and they have to dock, they are using thrusters, but they are small thrusters. They are very tiny adjustments. You have to get in line with the docking port. You have to do it at the right velocity, otherwise you have a collision, for example, or you just go by and you don't dock. So these require very small thrusts. So these are the two ends of the spectrum, if you like. And of course, reality is, it doesn't matter what kind of engine you have. You turn it on, it stays on for a while, and then you shut it off. You may have a constant thrust. Maybe the thrust has some realistic profile where if this is thrust, you turn it on and it will take some time to get to a regime value. Maybe that's kind of constant. Maybe it will fade away once the fuel is over. Or if it's a solid type of propellant, you just have to wait for the propellant to be over, or you can shut it off if it's liquid. But reality is that there is a duration for the thrust, right? of course. It doesn't matter how short it is, that's the reality. Well, we're engineers, so we try to ignore reality if we can, and try to come up with simplified models for that still work. And so we're going to start from impulsive maneuvers. Which mean a change of velocity of your spacecraft, the velocity vector in general, without change in position. And I should add here an instantaneous, of course, instantaneous. In other words, you have some kind of very powerful rocket engine that you turn on. The duration of the burn is so short that you can assume it's just giving you what we call a delta V, and I'm going to call the delta V as a vector, a change in that velocity from V1 to a new velocity V2. And that happens without a substantial change of position. The thrust is quick, intense, it's an impulse. And the position, you can assume it's kind of the same at the end of the thrust. If you think about a low Earth orbit, the ISS takes 90 minutes to go around, and that's really one of the lowest that we think about. So anything above that has a longer period. You stay on for 30 seconds, a few seconds, a minute. It's still an approximation, because in a minute the ISS covers 7 kilometers. But it is something very good for preliminary design of your maneuvers. Why is this so nice to do? Why do I care about assuming that it's instantaneous and I can change the velocity right away? What is it that I don't have to do? Remember that if I give you a position vector and a velocity vector, you can tell me right away, you can go to orbital parameters, for example. So that means you can tell me the shape of the orbit, its size, its orientation in space, and where the satellite is on that track. And so if you go from here to a new set of positions and velocities by just changing this guy here, you have a new set of orbital parameters immediately without bothering integrating the equations of motion. That's basically what you avoid doing if you say that you have an instantaneous thrust. Does it make sense? So all of a sudden, basically, your satellite is there, and you say it was a circular orbit. All of a sudden, it becomes an elliptical one. Magically, that's what you do in the same instant of time. That is the assumption behind impulsive maneuvers. That's all we do. Again, you need to have a pretty strong engine to do that. Now, in terms of delta V's that you can get, these also can be classified. I'm just giving you some nomenclature that you can find in the books. The very first one example that we're going to see falls under the category of pumping maneuvers, which means the delta V is parallel to your initial velocity, V1. So you're only basically increasing the magnitude of that velocity or reducing it. It doesn't matter. You're not changing the vector in terms of direction.
With the impulsive maneuvers, do we make the assumption that the time difference between making that impulse is so small compared to the entire orbit?
It's basically zero. It's impulsive. You know, an impulse is infinite thrust in no time. Yeah. Yeah. It's of course an approximation. But yeah, if it's, you know, a couple seconds and you have a very powerful engine that gives you, I don't know, many thousands of pounds of thrust compared to an hour and a half or more, it's a reasonable assumption. So probably if you do this is a good exercise. You can go into your numerical integrator of even just this equation here, right? And you can check what happens when you take a profile of thrust that is actually, you know, at some point in time, T1 goes all of a sudden to a value, stays there for a finite duration of time. T2, integrate the equations of motion with these and see what happens. And then actually take what would be the velocity at the end of this, T2, from that integration, and just assume that it's changing suddenly at time t1 and see how the orbits are going to differ after the fact. If this duration is relatively short and this thrust is big, you're not going to see probably too much of a difference. Yeah, there's an error, but it's probably acceptable. Depends on what you have to do. If your goal is, at the end of the maneuver, being exactly on top of another spacecraft because you have to rendezvous, then it may be a problem to have this approximation. But usually that's what we do. Even the space shuttle to go to the ISS went through a sequence of burns based on Hohmann transfers, which is something that we'll see in a second. They are designed assuming impulsive maneuvers, and then the last phases are corrections. Yeah, with much smaller thrusters. But yes, that's exactly what we say. No time, all of a sudden you change velocity. So pumping maneuvers, you either increase your velocity or decrease it instantaneously, but you don't change its direction. The opposite, I guess, kind of case is the cranking maneuver. The magnitude of velocity remains the same. So V1 before the burn is the same as V2, but the direction of the velocity has changed because of whatever reason that you have. A very simple one is changing the plane of your orbit. If you change the velocity direction, as you can imagine, the plane of your orbit is going to change. Because, think about this, h is what? Is r cross v. H is that vector that gives me the plane of the orbit. If I change the v to a different direction in space, h is going to change direction. I've changed the plane. Those are very expensive maneuvers usually. We'll see them later on. If, for example, you are living at the equator and you're launching from there and your satellite is going to start probably in some kind of equatorial orbit, but your goal is putting it at 63 plus degrees Molniya inclination, good luck with that. That's a lot of change in degrees. I think the space shuttle was equipped with fuel to change a couple of degrees at the most about its orbital plane. They're expensive because you have a velocity vector that is, I don't know, 7 kilometers per second in magnitude, and you want to change it to be the same, just at an angle, alpha. This is a big fraction of that 7. It's not that small, what you have to create. It's usually an important amount of delta V. And then you can have, I'm not going to write it, but of course you can have combinations of these two where you're changing magnitude and direction of the vector at the same time. But as we will see, these maneuvers are carefully planned. Not very often we change the magnitude and the direction at the same time. We try to sequence maneuvers in an intelligent way because of the following reason, which is this equation right here. Now this comes from propulsion classes that you may have seen. It's one of those equations that give you basically how much you're consuming for a given maneuver. Okay, so this will be the spacecraft mass before the burn. I don't know why I switched to italics. I have no idea. Delta M is the fuel consumption, is the mass you're ejecting from your thruster, so I just called it fuel consumption. I switched again. Look at that. This is a test. Can you understand both writings here? Yes? Okay, good. Are we familiar with these other things here that go into this exponential? So delta V is the norm of your, of course, your delta V. And if you go on through multiple maneuvers, you just add them together. So it's the magnitude of all the variations of velocities you created. The G0 is, we said what this is, we said what this is, we said what delta V is. G0 is gravity, acceleration of gravity at sea level. And finally, have we ever heard about ISP? First time? Really? You haven't taken propulsion? We don't do this at propulsion? In propulsion? Specific impulse. So someone has heard of it. ISP, which is measured in seconds, is defined as, I'm just going to write it here, the magnitude of thrust, I'm just going to call it T, and the rate of fuel ejection from the engine itself, I'll call it m dot, and all this is measured at sea level. So this is a quantity that people define for a specific type of engine, solid fuel rocket, liquid fuel rocket, ion thrusters, electric thrusters, whatever it is that you have. This is given through experiments on the ground at sea level, measuring thrust and how much mass is coming out of the engine per unit time. So that is a very important parameter to remember, because it's basically giving you the efficiency of your engine. As you can imagine, if I fix the mass consumption, how quickly I'm burning fuel, that m dot is fixed, and I can get for the same m dot more thrust, I have a more efficient engine, and vice versa. Fix the thrust and you can improve the engine so that you consume less, you have a more efficient engine again. Now, as technology evolves, we get engines with higher ISPs, but as everything in life, there's always a trade-off. Usually the ones that have very high thrust consume a lot of fuel. The ones you use for orbit to go to orbit have an ISP, I believe the shuttle was around the 400 seconds. Don't quote me on that, but that's the order of magnitude, 300-400 seconds ISP. If you go to a very tiny electric thruster that you can even mount on a CubeSat, on a small satellite, they can have numbers around thousands of seconds for ISP. Very efficient, but the thrust you get, it's tiny. You're talking about millinewtons or less. Again, the easy parallel is sports cars. You want a lot of performances, you want to go fast, you want torque, go to the gas station. Or otherwise, if you want a car that doesn't cost as much in fuel, you get less performances. That's what we have. And those are improving over the years, but that's basically a measure of how efficient is your engine. So a higher ISP will require less fuel consumption to get the same delta V. But it may require more time. At the end of the day, it's a matter of time. If you have time to perform a certain maneuver, you can do it with less fuel. To give you an idea of these values, let's see, I have some numbers. If you plug in a delta V of around 1 kilometer per second, which is a pretty important maneuver. Everything above 1, we'll call it a drastic maneuver. It's an important change of velocity. This requires, with the typical ISPs that you would have for the engines for these kind of maneuvers, this requires you to burn 25%, more or less, of your spacecraft mass. Which means you turn it on, you change your velocity of an amount of 1 kilometer per second, which is big. It's 1/7 of the orbit of the velocity of the ISS. So it's an important maneuver. But 1/4 of your spacecraft mass has been burned. It's gone. So as you can imagine, there are maneuvers that may require more than that delta V, as we'll see in a couple of examples. You may go to numbers that seem pretty scary. 60% of your mass has to be fuel. So imagine being in a car where it's just you and a fuel tank. You can't have a passenger. That's really what the problem is with spacecraft. There is no refueling stations. People talk about those, but they don't exist yet. And at the end of the day, you don't want all that fuel. You don't want to bring up all that fuel because it's less payload that you can have. The total mass of your spacecraft is what it is, but if you have to dedicate 70% of that to fuel, there's less experiments or whatever that you have to bring into orbit that you can have. So that's why maneuvers are planned very carefully. And once you're done with fuel, you're done in general. The geostationary satellites that are up there for 10, 15 years, after that, they don't have any more fuel. They have to dedicate that last burn to get out of the geostationary belt. And Patrick will probably talk to you about that. Okay, so let's start with the first obvious. Do you have any questions about this? Impulsive maneuver that you find in textbooks, which was used by the shuttle and is still used to get to the ISS. It's called Hohmann. from a gentleman called that way, transfer. This is a very first one, we'll see, very basic, is the most efficient maneuver to go from a circle to another circle. Small circle to bigger circle and vice versa, with two impulses only. So let me sketch a few things here. Your planet is right here, and say, just for the sake of an example, that we're going from this circle here of radius r1, so we're going from small to big, it doesn't really matter, to this other one, radius r2, and I'm going to call the first circle trajectory 1, second circle trajectory 2. What you do in a Hohmann transfer is you start basically from any point, from the start trajectory, in this case 1, you change the velocity, transfer instantaneously on a half of an ellipse, such that its perigee corresponds to, or periapsis, if you, let's start calling it periapsis, corresponds to R1, and the apoapsis corresponds to, is going to touch the other circle, corresponds to R2, right? So we start from, let's say, this point A and point B. So this is clearly talking about pumping maneuvers, because here what you have to do is you start from a velocity, let's call it V, at point A on trajectory 1, okay? And to leave that trajectory and go on what I call 3, which is this ellipse, I need to increase the velocity, and I'll show you why in a second. So you have to go to V, still in point A, because again, we said we don't change position, we just all of a sudden change the velocity, 3. So VA3 is greater than VA1. And this comes from the, finally, we use it from this equation. The mechanical energy per unit mass, or the specific energy, minus mu over 2A, is V squared over 2 minus mu over R. Okay? For now, we're going to do closed orbits. This is a physical quantity. The same major axis is positive, so the energy is negative for circles and elliptical orbits, and it's always negative, and is more negative as you go to smaller orbits, smaller same major axis. As you go bigger, this increases. It remains negative until you open the orbit and it gets to 0, parabola, and then positive hyperbola. But for now, that's what we're doing, negative. Now, imagine what is happening. I want to go from, this doesn't change, right? At point A, I'm not changing the radius. The position where I am is where I am. So the radius that connects E, center of the planet, to the position A is not changing. This piece is not changing. What I'm trying to change is this, is the same major axis. Before I accelerate with my delta V, so this change here is basically your delta V, right? This is what you have to provide. Before I do that, my 2A is what? Is 2R1. So before the burn, 2A is 2R1. After, what is it? Nope. What is 2A is the entire length of the major axis. It's not the same major axis. It's the axis is the length between apogee and perigee. So it's R1 plus R2. We see that? Now, which one of the two is bigger? This, right? Do you see that? Okay. So imagine substituting 2A before and after the burning here. If you keep this constant, if you go from 2R1 to R1 plus R2, your denominator is bigger. It increases, which means this number increases because there is a minus in front of it, right? So I have to increase the velocity. There's no other way. Is that clear? No. If my energy was before the burn, this component, I'm just coming up with random numbers that don't make any sense, but it was minus 4, negative, right? And after the burn, I need it to be -2 because I want to transfer to a new trajectory whose same major axis is bigger. So if I was divided by a certain number, I increase that number, that's what happens. Yes?
Is R2 the distance between the E and the big orbit, or the end of the small orbit?
It's a radius of a big circle. So what I'm claiming is trajectory 3 has these as its 2a. 2a of trajectory 3 is R1 plus R2. Okay? So is it making sense that I am increasing the denominator of a negative fraction, which means I get a bigger number actually. Magnitude is smaller, but there is a minus in front. So to go from this to this and keeping this piece constant, whatever this is, I have to increase this, the velocity. Now the same kind of reasoning goes here. I get on on a elliptical orbit at this point. So whatever is my velocity in B on trajectory 3 has to be increased to velocity B on trajectory 2, which is the circle. And the same goes because, so this was maneuver at point A, right? At point B, the before is now what was the after here, right? The before is the R1 plus R2. And the afterburn, same major axis that I want, or not same major axis, actually major axis, I guess, 2A, becomes 2R2, which is bigger than R1 plus R2. Okay? It's this entire distance, the big circle's diameter. Same. Go to your energy equation. The only way to go from this trajectory, leave this trajectory and become circular, since you're not changing your R, your position in B, this term here, it's increasing velocity. Is this clear? This is the core of how we're going to design these delta V's. This is how you compute them. You look at a point, you look at the velocity on the old trajectory, you look at the velocity you need on that same point to be on the new trajectory, and you subtract, or you do what you have to do. In this case, they're parallel, and you have to just speed it up in both cases. And it makes sense. You're going, think about it at a higher level. What you're doing, you're going from a certain value of energy to a higher value of energy to an even higher value of energy. Speed it up, and that's it, twice for this case. Now all this reasoning applies if you're starting on the big circle and you go into the inner circle and you do this other piece of the trajectory. You will get the same magnitude of the delta V, except here you have to slow down. Once you get to A, you have to slow down once again to circularize and go back to the small circle. But it's symmetric. It's just doing the opposite. Do you have any questions before I do something else, still on this? But this is really the core of impulsive maneuvers. I am at a point, I'm going to change all of a sudden the shape of my trajectory because I need to, because I want to. Yes?
How do the units work out?
How the units work? That doesn't have dimensions, of course. Yeah. This doesn't have dimensions.
So it looks like it's meter per second over meter per second times meter per second squared.
This one?
Yeah.
So delta V is meters over seconds, ISP seconds. This is meters over seconds squared, so that's adimensional. Everything is adimensional.
Oh, right.
Yeah. Yep. That's a good check, though. Always check your equations. Yeah.
Also on the topic of units, like thrust over mass flow rate, you have newtons over kilograms per second. How does that convert to seconds?
Yeah, that's what.
Oh, that one?
Yeah.
How did I define it? Let's see. Thrust. Oh, I'm sorry. Well, thrust is measured in pounds. That's usually it's thrust measured in pounds. That's a good, yeah. Because this is the way, this is mass over seconds. That's right. So the mass has to go away. It's mass in pounds, yeah. Or mass thrust in terms of weight. You can say pounds or kilograms or whatever it is. I mean, when you watch those videos when they're launching satellites, they usually tell you what is the thrust in pounds or in kilograms. Well, in pounds usually. Yeah. Thank you. Yeah. So this has, if it comes out to be seconds, it has to be that way. Yep. Any other questions? Okay, so one more step about Hohmann transfer, and then you just do an example, numerical example, just to convince you that these things are expensive. They take away a lot of the spacecraft mass, and you don't get it back. If we really want to go one step ahead of this, how do you compute the delta V's? Well, it's pretty simple. You get that equation right here, the energy equation, invert for velocity. Velocity, the speed, becomes square root of 2 mu over square root of 1 over r minus 1 over 2a. So the way you compute your delta V's, again, you put yourself at the first point, the before, you substitute into A what it needs to be there, 2r1, you substitute into r1, well, this is a constant, and that's your velocity, A, what did I call it, on trajectory 1. So that is square root of 2 mu 1 over r1 minus 1 over 2 r1. Velocity in A now on trajectory 3, which is the ellipse, the transfer ellipse, that's how it's called, because it's transferring from one to the other, r1 plus r2, and of course the difference delta V in A is, since this is a pumping maneuver, is simply, if we're talking about magnitudes, that's what you do, right? But be careful. You can do this when you know that the vectors are parallel to themselves. In general, the delta V is velocity after minus velocity before. And these A and B don't mean A and B there, okay? After, before. They are vectors. In general, that's what you have to do. Now, of course, if you know that they're parallel, you can just do your own thing with scalars. And the same goes for B. Now, this can be generalized. You don't have to go from a circle to another. Let's go from an ellipse to another, maybe. The line of thinking is exactly the same. So let's look at just one numerical example that I got, I think, from your book. I have a spacecraft that starts at 2 tons, 2,000 kilograms, and the initial ellipse around the Earth is flying on is given as 480 by 800 kilometers. Now, if I'm giving you these kind of numbers, what are these? There's no choice. Are those radiuses? You don't know?
Some on major axis and some on minor axis.
Height. There's no choice. The radius of the planet is approximately 6,378 kilometers. So anything I give you that is less than that better be a height, something outside the surface, you know, above surface. So I don't remember the language in the book or what I got this exercise, but yeah, that was called height. The perigee was at this altitude and the apogee was at this altitude above the surface of the planet. So basically the satellite is starting from this ellipse with those dimensions. And where do I want to go? Okay, I want to go to a circle outside of this. Now this is not to scale at all. But I want to go to a circular orbit, which I'm not going to draw entirely, with radius. So the final, where do I put it? Final orbit, circular. And again, the height is given here, and it's 16,000 height. Now, this is a big maneuver, of course. Again, it's not to scale, okay? And I want to do with the Hohmann transfer, 2 burns. Can I do that? Sure. I think the book tells you, actually there's not only one way of doing it if you think about it. The circle is going this way and it's also going this way. There's infinite ways of doing this. But again, we're starting simple. We're starting with pumping maneuvers, 2 burns, so we're definitely going to do that. But I mean, I could start here and can go on this ellipse, which is a terrible ellipse, but it's supposed to be an ellipse, and start at this point. Let's call it A, and basically create an ellipse that has the periapsis at A and the apoapsis at B on the circle, which is my goal. By the way, when you do these maneuvers, of course, those trajectories, where they touch each other, they are tangent, of course. Otherwise, the velocities cannot be parallel. So if my drawings are misleading, it's because I'm not that great at drawing, but this is tangent, okay? It's coming in tangent. This ellipse has to be tangent. And the same here. Is that the only way? I could start here, right? And go to the other side. Yes?
Wouldn't you always do that, leaving perigee though, so you have a higher initial velocity? The highest possible initial velocity?
If I do that, yes. In this case, that's what I'm doing. We don't probably have time to do it today, but I will generalize this to show you when is best to leave here in terms of consuming less, or leave here. Depending on the relative sizes of the orbits involved, there's some considerations we can make to choose if it's better to do it at the highest velocity point or not. Yeah. So you could start here, which is the apoapsis in this case, and just do it the other way. If you don't really care about being in at a specific time in a specific location on the circle, you can really do it this way. No one tells you that you cannot start here, go on some, I don't know, weird trajectory that happens to be some portion of an ellipse that intersects your goal trajectory, and then do a combined pumping cranking maneuver. You can do this. You can correct here. You can do the same here. You can maneuver from any point in principle and do 2 burns. You can do that, but we're not doing it for now, and it's usually not convenient to do so. But so let's say that we start from A, the periapsis, and we go to B. So it's 2 burns, 1 here, 1 there. Do you need to speed up in both cases? What do you think you have to do? You speed up for both. You're going to bigger. The same major axis of the transfer ellipse is smaller than the same major axis of the goal trajectory. It's definitely bigger. So forget about this one intermediate. So I'm doing this trajectory, right? So I'll go from 1 to 2 on trajectory number 3, which is my transfer. Same major axis, or the entire major axis of 3 is bigger than the start, so I have to go and accelerate. But the trajectory 2 has a diameter that is bigger than the distance A to B, so like before, I have to accelerate again because of that energy consideration we just made. You agree? Okay, so I have the numbers here. So velocity on point A, trajectory 1, so the ellipse, is, according to that expression, is square root of 2 mu times square root of 1 over the radius, the distance from the center of the planet at point A, minus 1 over 2, whatever is the same major axis of that. What is the same major axis of this? Or the 2A, the whole thing? Yeah, it's the 480 plus 800, which are the heights of apogee and apoapsis and periapsis, plus planet. If I gave you the heights, this is an easy trick to have students making a mistake. Just give them the heights and they forget about the radius of the planet. I do as well. I mean, I'm guilty of that as well. But you need to be careful about looking at the numbers. So that should be it. And so these, if you do it, ends up being 7.7104 kilometers per second, similar to ISS. Okay. What is the velocity A? Now I'm going from 1 to 3, the transfer ellipse. Well, still square root of 2 mu, still 1 over RA because it's an instantaneous maneuver, don't change the position, minus, what do I put here? Well, it's whatever is the same major axis of that trajectory, right? And so if I want to do twice the same major axis, is the distance between A and B, which is 480 plus 16,000 that I want to achieve plus twice the radius of the planet, right? That's what it is. I have, what do I have? Let me make sure I'm copying the right number here. I gave different names to trajectories. This should be the one. I have to speed up, so this better be higher. 9.433 kilometers per second. I'm doing all in scalars because, again, I don't change directions of velocities. Guys, stop me if you have any questions. This is basic theory we need to understand. No questions? Okay. So the first delta V in point A is VA3 minus VA1. And when you do these exercises, you can name the trajectories the way you want. The fact that I call 1 my initial trajectory, my initial orbit, and the goal I want to achieve, I call it 2, and then the transfer is called 3, it may be confusing for you, so you want to do something else, do it. As long as you remember the names you've given. For example, here I have a different way to name them, of course, just to confuse myself. What is that? It's about 2, it's a little less. No, it's more. So, no, 1.7226, yeah, it's less than 2, kilometers per second is my first delta V. So if I'm using a, oh, I didn't give you that. Did I give you that? The ISP, do I have it at the end? Yeah, let's say that the ISP is the typical value that I mentioned before. ISP is 300 seconds. So with that kind of order of magnitude, this is already eating up, I don't know, 30% of your mass of the spacecraft, just this burn. Okay, the second delta V velocity, let's see, I call that B. So B, I arrive on trajectory 3, is square root of 2 mu over, what is that? 1 over radius at B minus 1 over 2, well, I'm still on trajectory 3, right? It's the same. So this hasn't changed. The RB is now 16,000 plus. Not 2RE, right? This is now radius. It's not a diameter or major axis.
How did you find 283?
Which one?
283.
283.
It's 480 plus 1600 plus 2RE.
Yes.
Would you include the 800 as well? Or
No.
by the
No, okay, so 283 would be, it's the major axis, is this distance, right? From A to B. So A was the periapsis on my start ellipse, which was at a height of 480. So basically the distance from Earth to point A was R of the planet plus 480. Point B, I want it to be a 16,000 height, so 16,000 plus RE, because you have to do the whole distance. Make sense? No. Yeah, that's it. So this one is, this is less, 2.8, better be less, it's the apoapsis, 89 0.08 kilometers per second. And finally, the velocity at the point B on the trajectory I want. Instead of doing that, can you just give me right away the expression for the velocity on point 2? Circle, right? Okay. So this is 4.22044 kilometers per second. So the delta V you have to have at point B. So this was point A, the first impulse. At point B is velocity, trajectory 2 minus velocity, trajectory 3 is 1.3297 kilometers per second. Now, if you use the ISP I gave you and use the formula I removed from the board, which is delta M over M equals 1 minus E to the minus delta V over ISP G0 times G0, okay? I get, what do I get? I get that my delta M, if you do your calculations, is 1,291 point something kilograms. This is more than 60% that initial mass.
You just combine the two delta V's?
Yeah. Delta V total is, delta V, that's a good point, is delta V A plus delta V B. You just take your delta V's, take their norms, add them together. It doesn't matter if one is accelerating, one is reducing the velocity. It does not matter which way they're pointing in space. You take their magnitudes and add them together because each delta V is you turning on an engine. It doesn't matter where you're facing that engine, you are expelling fuel. So that expression has the total delta V. That was a good point. Thanks. Okay, so I think I do have the total. What is it? It's 3 points, so it's about 3. Where is it? Okay, 3.0522 kilometers per second. So according to my calculation, is 64% of the mass, which was 2 tons, goes into fuel. Goodbye. That's a lot of your weight, right? It's a big maneuver. I mean, you're raising to 16,000, but this is not even close to geostationary height, for example. It's not even enough for a GPS satellite. Yes?
So does the NASA spacecraft initial, is that including the weight already?
Yeah, it's everything. It's wet mass.
So you're assuming that you're going to minus the mass later after the mass?
After the fact is less than 800 kilometers.
It looks like 700? Okay.
Yep. Now, I don't have the numbers in mind for the space shuttle, but you can imagine the majority of what was taken off was fuel tank, fuel, solid rocket boosters, and that's gone after you are into orbit. So I don't remember the percentages, but I wouldn't be surprised if more than 50% is gone the moment you are in orbit. So if you call the space shuttle and the astronauts and their satellite, whatever they had in the payload bay, your payload, I wouldn't be surprised. We can look it up. That more than half was gone just to get there. Yep. Yeah, so it's impressive. Unless we get a way to increase these without decreasing the thrust that you can get. That's the problem. Then, yes.
So I don't want to go off on a tangent, but isn't the rocket equation, doesn't it equate the mass of the fuel that's coming out, but also the velocity, the exit velocity?
That is basically a measure of your exit velocity. The ISP, if you look at the engine tables that you can find even in your Astrodynamics book, and probably there is one, usually high ISP means high ejection of the gases, high velocity of the...
So my question is, could you talked about efficiency earlier, but could you expel a smaller percentage of your spacecraft fuel by having an engine that puts that fuel out at a higher velocity? Or does it always equate to that percentage?
So yes, the thrust equation is basically, just to make it simple, is a product of how much mass you push out and its speed, relative speed to the body of the spacecraft. It's a matter of technology. You can push masses out very quickly, but usually what happens is as you go higher with the velocity of ejection of the gases, the amount of material you can eject goes down because of limitation of technology we have, the nozzles we have, the fact that we have to cool them down. As you want to accelerate them, it means that you have to heat them up more. And that means they get to the throat of your nozzle with an even higher temperature, and you have to cool them down, which is more mass on your spacecraft. So it's a technology issue, and I'm not the designer of thrusters, so you would have to ask someone who designs those. But basically, you hit a limit of materials, you hit a limit of additional mass that you end up adding to obtain that kind of speed at the end of the nozzle. But yes, that is basically what you would, ideally you would like to basically take, I don't know, 1,000 kilograms per second that you want to eject, and those gases have to be as hot as possible to get more thrust. But yeah, it's basically the technology of the engine, how it's designed. Yes?
Should we like redo the math with a different mass after the first launch? Like after the first impulsive, should we have less mass so we would need less?
You could. You should get the same stuff.
Really? Mass?
I think so.
Because it's a very significant portion of the mass in the first part.
Yeah. You should get the same. Try it. That's a good point. Does it make sense what he said?
You lose like more than 50% of the mass from just the first orbital.
No, here, what I'm doing here, I'm just adding all of them together. At least in my calculation, to give you an estimate of these, I'm adding both of them. The delta V's, I add them together.
Well, I was thinking, if you just did the individual calculations.
Whoa, time is over. Sorry. No, go ahead.
The delta M in your first maneuver will be some sort of number, and the delta M in the next maneuver will be another number.
Yeah.
So assuming what you did was sum of the delta M's is what you get here is what correct.
Yes. Yeah, you should get the same. You should get the same amount. I mean, I haven't done, I can redo it to validate, but you should get the same. Yep.